Okay, back once again. This video here is going to discuss and give examples of process of implicit differentiation. And before I show you how that works, we want to understand what we mean by this idea of implicit differentiation. And so, first of all, we've got to deal with types of equations that we're going to be using. I have a pretty simple one here. This is the equation x squared plus y squared equals 1. It is just the equation of a circle with a radius of 1, centered at the origin, and there's its graph, okay? Sometimes we call this the unit circle if we were studying trigonometry. And y is not an explicit function of x. Okay, it's pretty obvious here that this graph does not pass the vertical line test. So I'm not dealing with a function here with this equation. However, if I would look at y, and it's not always possible to do this or easy. Sometimes we get equations that are much more complex. So that's why I'm going to that's why I had a simple example here. If I solve for y by subtracting x squared from both sides and then taking the square root, I get plus or minus this thing. So I get y to be one function. So in other words, y is now a function, this value for y, if we only consider the top part of the unit circle. And then if I consider the bottom part, the case where this radical is negative, that is the bottom part of this. So if I take them separately, one at a time, this is a function of x. Y is a function of x here, and y is also a function of x here. All right. So what we say is that y, has a is not an explicit function of x, but an implicit function of x. In other words, two or more separate functions of x, we express y as. Okay, so we have more than one function here. All right. So now, if I get into this on the next screen here, notice if I graph the top part, you could see the red graph and the bottom part, the blue. Okay. So that's just summarizing here, explaining how y can be a function of x if we consider two functions of x, okay, two separate functions. All right. And so what we're going to do here, this is just kind of get into this process and show you how this works, is we follow this three-step process here to find its derivative, okay? So we know if we break this up, we got two functions. So we're going to find a derivative or an instantaneous rate of change here. And here we go. All right, to differentiate both sides of this equation with respect to x, keeping in mind that y is assumed to be a function of x. So in other words, when we have this original equation, I don't have it here, I don't want to scroll back, but x squared plus y squared equals 1, we're just going to differentiate both sides of that equation with respect to x. Then, using algebra, we want to place all the terms with dy dx on the same side of the equal sign. So in other words, if we're finding the derivative of y with respect to x, we need to use the chain rule because, again, we're assuming that y is two or more functions of x, okay? So we need to use the chain rule on the terms that contain the y. And then lastly, all we really need to do is solve for dy dx, and I'll show you how that works here, okay? So that's basically, what implicit differentiation is. And we're going to also find that, some of the other word problems that x and y can both be uh, functions of a third variable. And a lot of the problems we're going to be doing, they're a function of t, which is time, and x and y are changing with respect to time, but they still have this relationship. And that's kind of the practical application here. And if you already did the problem involving elasticity, we already used implicit differentiation for that. So I recommended watching this video first before you took on those problems. Okay. But anyway, let's move on to an example or a couple of examples here of finding implicit differentiation. I think I have these are the ones. Yes. Okay. All right. So let's move on here. So what I want to do is, find dy dx using implicit differentiation. Okay, so this would be the solution here for this particular one in my math lab. Okay, so how do I start with this equation and find dy dx using implicit differentiation? Well, again, following the three-step process, number one, that's just an eraser mark here. I want to find the derivative of this equation. I go through term by term, both sides of the equation, term by term, and find their derivatives. So I got 15x squared here, pretty straightforward. 14y, I don't know, that must be a stray mark there on my scan. 14y, because this is just 7y squared. Okay, so just ignore that. I don't know if I can even get a little, oh, no, I don't know. We'll wait on that. But anyway, 14y dy dx, that's using the chain rule, right? Because I got to multiply by the derivative of y with respect to x. Okay, think of that as a composition of functions. And then this term right here, the derivative of 9y is just 9, but again, using the chain rule, I have dy dx. So the second step would be isolate all the terms with dy dx on the same side, which they are naturally, okay? So then I factor this out and divide both sides by this expression. So all I did was just treat this as one entity, dy dx. I factor it out. I leave behind a 14y and a 9, and then divide by that expression, and I get dy dx equal to 15x squared divided by 14y plus 9, okay? So if I did graph this equation here, this would give me the instantaneous rate of change of y with respect to x. In other words, if I had my x and y, coordinates as I know, or axes as I normally would, it would give me the slope of the tangent. To find the point, though, I would have to find a point xy on that function and substitute those values in. Okay, so it would have to be a point on the graph, and I would have to plug in both the x and y to get the slope of the tangent. Okay. And then obviously I would have the point at that point. I can find, the equation of the tangent line there as well. Okay, so that's what I could use this for. Again, this equation has really no application or context here, so we're just staying pretty basic. Okay, so here's the other problem. It gets a little bit nastier in terms of the, I'm going to give you at least one example, with some a little bit more challenging in terms of the algebra and so forth. Okay, so whenever you're dealing with radicals here for one like this number 6, it might be best just to write them with rational exponents. So I write the square root of x as x to the 1/2, and the same with the y here. And I just use my power rule here. So 1/2 times 2 just gives me 1, and subtract 1, I get negative 1/2. Or 1/2 times 12 gives me 6. Again, subtracting 1. But remember, I have to use the chain rule. And basically, just write dy dx after each time you take the derivative of a term with respect to y. And then, of course, over here, I just have 7 dy dx. Okay, now I don't have these terms on the same side. I did some simplification here where I just converted back to radicals. So again, the negative 1/2, that would put y to the 1/2 in the denominator, and just wrote it as a square root of y. And I did the same thing over here with x. Again, use pause and scroll if you need to stop and go back over that again. And then I'm going to go ahead and I just subtracted the 7 dy dx from both sides. I could have just as easily moved this over, but I wanted to try to get the answer to look like they did. So this solution here could look a little bit different, okay, but essentially be the same thing if I chose to go the other route and move the 6 over square root of y over to this side and then factor out. But I moved the 7 over here, and then I moved this term over here, so now that became a negative 1 over square root of x. Then I factor out my dy dx, so I leave behind 6 over square root of y and negative 7, then divide by that quantity. Okay, so really when I'm here, this is a solution, and it doesn't look like this. Okay, I believe in my math lab, if you would type this in, it would give you a correct response. However, probably would be a little bit more challenging to enter this solution than it would be to enter this one. And so what I did was just use basic rules from algebra here. I multiply by the LCD of all the little fractions, which would be the product of the square root of x times the square root of y. So notice that here I just wrote it as square root of y times square root of x over square root of y times square root of x. I'm not changing it. This is just a number one. So when I multiply through here, I get what I want. The square root of x's cancel out, and I'm just left with a square root of y. And I just wrote my negative out front here. That's where this is coming from. And then when I multiply here, I got to use the distributive property. So the square root of y's cancel out, and that leaves me with 6 times the square root of x. And then over here, I just have, well, there's nothing to cancel out, so I just have negative 7 times square root of x, square root of y. And then all they did here, clean that up, is just factored out a common factor of the square root of x. So I take that outside, I leave behind a 6, and I leave behind a negative 7 times the square root of y. Okay, so there's your solution, and it matches up with my math lab. All right, so there you go for implicit differentiation. Again, pretty simple to, I would say, moderate. I'm sure there's a few more challenging ones in there. And again, of course, use the examples to maybe help you fight through that algebra. All right, that's it. And we'll see you next example for related rates.